So, it's a pleasure meeting you again. Welcome back. And now we discuss the electrical energy and power. Okay. For that, I take a conductor of a certain length, area of cross section, etc. It doesn't matter. But these are the points A and B. Here the potential is VA, which we call the initial potential, and VB, which is the final potential. This is positive and this is negative, so the current is flowing in and out of this conductor. Same current. So equal amount of charges are coming out. The time that it takes is delta T. Okay. Now, I told you that there is a certain thing that VAB is written as VA minus VB is equal to V. Okay. But delta V is written as the final value minus the initial value, which turns out to be equal to minus VAB, which is equal to minus V. Okay. And the charge that flows in time delta T, when the current I is flowing, delta Q is equal to I into delta T. Okay. Because I is defined as delta Q divided by delta T. Of course, delta T is the time interval. So let's see. What is the potential energy at A? It is delta Q into VA. Okay? And that at B is delta Q into VB, which I give the names UA and UB. So naturally, the delta of the U potential will be equal to the final value minus the initial, UB minus UA. So I take delta Q as common. This turns out to be equal to VB minus VA is equal to minus delta Q into V, as I told you. So this is equal to minus times I V, because it is I delta T is delta Q multiplied by V. I write it a bit musically, minus IV delta T. Of course, this will be less than 0. Okay. Now, in such an arrangement, when the charges are moving, okay, we'll say that the positive charges are moving from VA to VB and negative charges they are moving from B to A. Okay, because of their negative charge, they have to move from here to here, and if positive charges, which are not there, but if they were there, then they will move from A to B. Okay. Now, let us consider first of all that the charges are flowing like water in a rivulet. If charges move without collision, what will happen? The kinetic energy will also change. And then there is a rule, there is a law, and that is kind of universal, that there is a conservation of energy. So this delta K, the change in the potential energy, the kinetic energy, this will become equal to minus delta into U potential. So naturally I can write from here, and this becomes I V delta T, and which should be greater than 0, and kinetic energy is always greater than 0, 0 greater than 0. So the kinetic energy will increase, but the current is steady. The current is steady, it's not changing. No acceleration, Vd is constant. So what happens is collisions are occurring. Collisions are occurring. And the energy is shared with atoms. Atoms, ions, the thick ones, big ones. So what happens? When they absorb energy, then there are vigorous vibrations, more than what were there before. And when the vigorous vibrations are there, then the conductor heats up, gains energy, heats up. What happens to this heat? I told you one day that if the heat builds up, then the temperature builds up. ज़्यादा खाएगी तो मोटी हो जाएगी. Conductor heats up, and from the surface of the conductor, energy is dissipated. Okay? That's why I said that our resistor or the conductor is the Raja Beta. Whatever energy we give to it, that Raja Beta is spent. Okay. If the money 50 rupees per day, spent. 500 rupees per day is spent. Okay. Just will go out, eat it out. Okay. So energy is dissipated. And this energy dissipation, it appears in the form of work done, delta W. And naturally it is equal to IV delta T over here. So now we can define that the power is work done per unit time by basic definition of power, rate of doing work. So delta W upon delta T, you can see delta W upon delta T will turn out to be equal to IV. So we get IV. Now we have our friend Ohm's law, which is defined as the potential difference is equal to R into I. So if I substitute these values, so I will become equal to V upon R, so I'll get V square upon R, and V will become equal to Ri. I can substitute here and I'll get I square R. So this is what happens along with this appendix that is there. Together they give us the relation for power dissipation. Okay? So in the case of a steady current passing through a conductor, which we also call a resistor, there is the generation of power, and this power has to be dissipated, and this power is VI or IV I square R. I prefer to write is Ri square, but no, I square R is musical, V square upon R is also musical. So if I know one formula and the other formula, readily in the split of a half a minute, I can write all these formulas. So this is about the electrical energy which is generated and what happens to that. For example, this bulb is here. Okay, I am putting a current through it. So what is happening? The filament will get heated up. Or in the room heater, that we have the resistance over there that heats up, and at a certain level there is a dissipation. Of course, there should be some argument about whether the temperature will rise. No. The heat dissipated in the 1 kilowatt heater is less than that dissipated in 2 kilowatts, etc. We'll talk about that later on when we are doing some problems. uh, shortly. And now we talk further about this. So we have just learned that there is electrical energy and there is power. Question is, yes, you can ask me a question. Where from does this power come? Where from does this energy come? So the answer is that the current is made to flow in the circuit which contains a resistor or a conductor when we have a cell or a battery or any other source of steady power. But in the case of a cell or a battery, we obtain the energy from the chemical reactions that are taking place with it. So the chemical energy is converted into electrical, useful form of electrical energy, potential difference is generated, and a steady current is guaranteed by doing that. We'll have occasion to talk about that shortly. So, let us take the item combination of resistors, series, parallel, mixed, etc. It's very simple. First of all, I take the series combination of two resistors R1 and R2 in series, and the main thing is that the same current will pass through both of them. The potential difference which I have applied over here, this is going to be split in two parts, V1 across R1 and V2 across R2. Okay. And like a good boy, I am doing the equivalent resistor, capital R, V, I. Okay. So, there is always a current I and Chi, they are equal. Okay. So the key formula which we are going to use is V is equal to Ri. Okay. This is the Ohm's law. And what we find here in the series by inspection itself, that this potential difference V, which is applied here also here, this is equal to V1 plus V2. So I can write from this formula that Ri is equal to R1I plus R2I. I goes. So I am left with R is equal to R1 plus R2. Where of course this R is greater than R1 and also greater than R2, so the resultant is more than either of these resistances. Even greater than the greatest ingredient. I get this formula. R is equal to R1 plus R2 for the couple of resistances. In general, if I have n resistances, one after the other, same current will pass through this one, this one, this one, and the voltage will be divided V1, V2, Vn. So this is the formula that we get. Very simple. And this R will become, if all these resistances are equal to R0, then it will be equal to N into R0. Okay. So this is also understood very readily. In the parallel combination, again I take the case of two resistances first of all, extend those arguments to the general number of n number of resistances in parallel to each other. So what happens? This current I, here the potential difference across both of them is the same. And the current will be split in two parts. R1 has a current I1 and R2 has a current I2. So that the net current is equal to I again. Okay. Flows in, flows out. And so our argument will be that I will be equal to I1 plus I2. And from here I can write I is equal to V upon R. So I can write V upon R is equal to V upon R. We see that here we have the current I is equal to the combination, the split of the currents I1 plus I2. And this is nothing but the conservation of charge, this relation. So I can write from here V upon R is equal to V upon R1 plus V upon R2, and then V goes 1 upon R is equal to 1 upon R1 plus 1 upon R2, and when I take the LCM etc., I find it to be equal to R2 plus R1 divided by R1 plus R2. Right? So for the combination of two, we obtain a relation like this, that R is equal to R1 R2 upon R1 plus R2, which is product upon sum. Similar thing we obtain in the case of capacitors. In this case, this kind of a relation, R was equal to C1 C2 upon C1 plus C2, and here C was equal to here C1 plus C2. In general, if I have many of them in parallel and the total current is split in parts I1, I2, IN etc., then we find that 1 upon R is equal to 1 upon R1 plus 1 upon R2 plus upon and so on, and this is equal to N upon R0 if we have this thing. Okay? If R1 is equal to R2 is equal to Rn is equal to R0, etc. So I get, naturally we find that because N is more than 1, minimum 2 for the combination, 3, 4, 5 like that, so the resultant equivalent resistance is less than the original resistance. Okay. Now we wind up by taking the simplest case of mix combination, where we have 3 resistances R1, R2 and R3. Please don't say that R1 and R2 are in series. No, R2 and R3 are in parallel, and the parallel combination is in series with this. So this is equivalent to a resistance R, like we have been doing, and then even just by inspection I can say that R will be equal to R1 plus R1 R2 upon R2 plus R3, etc. There are many other things, there are many tricks, there are many topologies that we'll talk about. For example, in the case of Wheatstone's bridge, which I took in the case of capacitors, similar kind of thing will be taken up in the case of the various mixtures of various resistances, various combinations. And one thing that they may ask in this, that if the potential difference is equal to capital V, okay, and these values are also given to us, so what is I1 which is equal to I, and what is I2, I3, etc. So we just measure the potential difference over here divided by R2 divided by R3, etc., etc., like we have done in the case of capacitors. Okay. So this is in a nutshell, in a very simple form, an introduction to the series, parallel and the mixed combination of resistors, just similar to the case of the capacitors that we have taken before. But capacitors are the storage devices, whereas resistors are always Raja Betas, okay, the kings and princes of Tartary. Whatever energy we give to them, they will dissipate in whatever situation they are there. So they are energy dissipation devices. They dissipate energy in the form of heat, whereas capacitors can store energy, and the energy stored in the capacitor can be utilized by us judiciously. Thank you very much for being with me today, and shortly we meet again. Okay, inshallah. Bye.